Hi all, this is Amit and Georgin here. We are going to present a project on analysis of SaaS coordination strategies for supply chain performance improvement. So what is SaaS? SaaS is a software oriented as a software as a service. It's a software licensing and delivery model in which software is licensed on the subscription basis and is certainly hosted. It is sometimes referred as on demand. It is sometimes referred as on-demand software, and SaaS is typically assessed by using a thin client web browser. SaaS has become the common delivery model for many business applications, including Office and messaging services, processing softwares, DBMS softwares, CAD softwares, and ERP softwares. These also involved some of the managing softwares, human resource management also. So SaaS has been incorporated into the strategy of nearly all the leading software companies. So finally, the SaaS is on-demand software. It is cloud-based, and it can be offered as a single-tenant or multi-tenant system. So what basically is multi-tenant system is there is only one version of the system that is currently used by all the clients, and all of the data of all the users is stored at the one single database. And in a single tenant system, there are multiple versions of the software. Each customer will get a different database, so their privacy of databases increase, and it cannot be swapped with another users. So software as a service means you don't have to have a powerful software computer to truly do powerful things. So SaaS can answer questions like, how could my overall profit of the North Carolina can be impacted next week if I lower the prices of these beer 12 packs by $2? So these kind of questions can be answered by SaaS. With SaaS, you can kick off that analysis of your phone, tablet, computer, and any recruited dozens of servers in the cloud to calculate the answer for you. So until recently, you could even Google search over the text message. That means you could have used the phone made 20 years ago to perform the computing tasks utilizing 1,000 servers. So, application service provider and application infrastructure provider are two main components of SaaS. So, I'll explain what is that. So, application service provider, it is a prominent trend in the software industry in late 1990s was the development of the application service provider business models. So, ASPs offer their customer access to the software applications via network instead of installing them to the customer's in-house computer system. So ASP host manage applications from a central location and charge fee for their services. The best example of that could be a Self-Wrap. Self-Wrap is a cloud-based supply chain order management software that provides advanced order management across all the online channels and fulfillment locations, including automated order routing, print, pickup, ship, customer notifications, these kind of things. So working in the sync with the self-serve inventory management, shipping management, uh, customer management tools ensures the information is updated in a real time. And what is the application infrastructure provider? An application infrastructure provider provisions the computing operational infrastructure for developing, deploying, and managing the enterprise class applications. It houses all the physical resources for application through managed service platform. These applications include computing hardware, infrastructure operation and management software, network internet connectivity, and power coding. So after that, the role of SaaS in supply chain management. Supply chain SaaS can be very useful in forecasting, transportation, and decision support. Wholesaler usually do not have access to the customer's demand data. They may have a historical order data that performs the forecast. Therefore, the wholesaler might be forced to keep a higher capacity than the retailer in order to fulfill the delivery of the products whenever the retailer orders them. This leads to the higher inventory cost. So appropriate ASPs may transfer the linear supply chain in the adaptive supply chain network that enables all the partner to share the information, plan, and coordinate. Adaptive supply chain networks are designed to enable dynamic collaboration throughout the several processes, including forecasting demand. So the sales forecast delivered from those data can help. can help plan operation more effectively. In transportation, SaaS software can automate the transportation management by managing shipments, flow of goods, etc. While coming to the support systems are designed to assist the support to support the human decision maker in the decision making process. They provide the support for decision maker ranging from top executive to line managers in semi-structured and unstructured problems by bringing together human judgment and computerized information. So it makes the use of saved data to make decisions. Um, After that, we have an application provider value chain. So this is basically how ASP and AIP are integrated together and work together to maximize the profit for in the both sides. So basically, figure explains there is a AIP is the sum part of application, which is in providing infrastructure, and application service provider are providing the software to the clients. So to provide the application services to its clients, the ASP acquires computer capacity Q from AIP, who charges the W per unit capacity, and the ASP sells its value added service to the market at the price P per unit capacity, as we can see in the figure. The ASP faces the price sensitivity market demand for its services. So it will generate a random demand which is X, and then W per unit capacity is the capacity which will be decided based on demand. So if the demand is more, the infrastructure will be cheaper, as they have to produce infrastructure in bulk. So this is our first model, which represents the basic supply chain model. This model captures the specific features of the application service provider and application infrastructure provider. This model and results are general in nature that are also applicable to those service industries exhibiting the similar characteristics of ASP. There is a price sensitive random demand characterized by probability distribution. F of x is equal to x by p, and uniform distribution is assumed here for analytical traceability. So the application service providers expected profit excluding the overall over and under capacity cost is mentioned as below equation. So the first term in equation, it represents the expected profit when the actual demand is below the capacity or capacity Q ordered from AIP, while the second term describes the expected profit if the actual demand exceeds Q. So the expected profit is combination of both. So for another equation, while developing equation for AIP, the revenue of the application infrastructure provider equals to the computer capacity ordered by ASP Q, which is Q, multiplied by the unit capacity of price W. The cost structure of AIP has a two components consisting of the per unit cost of the computer capacity described by parameter C and the diseconomy of the scale cost parameter E. These are related to the management of infrastructure. The ASP's objective is to maximize the expected price by deciding how much capacity Q to buy from AIP and what price, which is at P, to change the market. The AIP is concerned with the setting an appropriate per unit capacity price, which is W, to the ASP in order to maximize its profits. So this is the main funda behind the this model. Because of the random nature of the market demand, cost associated with ordering too much capacity, which is called as overall over capacity cost, and ordering too little, which is called as under capacity cost, will arise. We define the expected overall capacity and under capacity as follows. So these are considered as a risk due to uncertainty. In these formulas, the R is considered as a salvage value of unused capacity, and K is considered as a cost of lost sale due to insufficient quantity. So we are developing the coordination strategies to apply some of the scenarios which has been developed, and the data has been generated or tested to prove this model, which one is the most effective. So the first scenario is ASP and AIP as a combined planner. So profit is combined for of AFP and AIP, which is similar to the newsbuy model. So the funda is that the basic ASP and AIP will be handled by the single organization. In another scenario too, AIP coordinates the strategy. This means that the AIP will face the client and they'll know the demand and all at the first moment. So ASP shares the pricing information and corresponding market demand to AIP, and ASP always order the maximum availability of the capacity. In this case, AIP also knows the infrastructure demand and what are the sales of ASP. So ASP will be easy for AIP to uh, to predict the future demand and maintain the inventory. In scenario 3, ASP coordinates the strategy. ASP does not communicate any capacity requirement and pricing decision with AIP. So AIP will have no clue how the demand would change in future, and they will have to maintain their inventory levels with their own knowledge. So AIP determine the price of capacity by scheduling, finding the optimal capacity that maximizes its profit. And the fourth scenario is independent strategy by AIP and ASP. Both ASP and AIP determine their own optical policies individually. So numerical analysis has been done to analyze the impact of below key parameters on the supply chain performance. In order to do the numerical analysis, we have considered the certain parameters. The first parameter is the price sensitivity parameter of expected demand. The another parameter is per unit capacity cost of AIP, which is C. Diseconomy of scale parameter for providing the capacity E, and the last parameter is range parameter of uniform distribution B. To analyze these four scenarios, we have used the results from numerical analysis. So the first graph shows the parameter of price elasticity of expected demand. In this case, competitive aligned is the scenario 4, which is competitive aligned, shows the maximum profit in terms of supply chain performance. In another scenario where the parameter is per unit capacity cost C, here also competitive align holds the maximum profit in case of the supply chain performance. In these other two graphs, diseconomy scales parameter is used or distribution range is used. So here also we can see that the competitive aligned scenario holds the maximum profit with respect to supply chain performance. So we can say that after analyzing these graphs, we can say that the profit is maximum, expected profit is maximum in case of the competitive aligned, which is scenario 4, where the ASP and AIP competes with each other.
We are discussing about the coordination strategies between the ASP and AIP without considering the delays or congestions. So even though the players have an incentive to deviate, it is always possible to create the high incentives for each player so that the outcome is also a Nash equilibrium. So while studying the coordination strategies, pricing model and capacity management issues between ASP and AIP, benefits of the communication between ASP and AIP is really easy to identify. However, realizing these issues and defining a coordination strategy under the influence of queuing effects is still an issue. So in the supply chain logistics, the demand from end user comes in the form of packets over internet. From the SaaS model, to be successful, these packets need to be delivered to the end users fast enough so that the delay in accessing the ASP service is minimum. Traditional supply chain does not consider the effect of this congestion, and the customer utility changes as congestion increases. As a result, the customer has to wait longer time in order to get this job done. And in addition to this, every new customer in the queue affects congestion of every other job that is already there in the queue. So in this new model, we will be discussing the congestion and its externality effects. So the goal of ASP here is to decide the optimum price and to sell the optimum price to sell, and also to find the optimum capacity of infrastructure that it should acquire from AIP. So for the AIP, the goal is to decide optimum price at which it should sell the infrastructure to ASP. Moving on to the model, we will, like, instead of analyzing the quality and the time to deliver as separate components, we'll model only the delay time as a measure of performance. The players ASP and AAP could reach a Nash equilibrium through proper coordination as we have discussed before. So consider that the AAP provide the infrastructure to ASP at a price W, and ASP sell this infrastructure or this say value added service to the customer at a price P per transaction. Let the AAP's marginal cost be C and the demand that ASP face in the market from consumers be a Poisson distribution lambda. So as we already know, for every queuing model, the service rate will always be higher than the arrival rate. So in this model, a customer who use the service will incur a transaction price, and in addition to this one, an additional congestion cost per transaction due to the delay in the queue also will be added. So this is what we are going to model in this one. So the congestion cost will be the product of delay cost per transaction and also the expected time a customer spent in the ASP system. So by taking the derivatives of equations, and we have modeled the profit of ASP and profit of AAP as you can see in the equations in slide. So for the ASP, the cost of managing infrastructure increases with the complexity of business model. So this actually is the diseconomics of scale parameter and is represented by parameter E as you can see in the equation 1. So for this model, we can conclude that the profit would be better when one player coordinates with other player than when there is no coordination between the players. Here we are discussing the strategies that is applied to the model with congestion. It is actually similar to the one which we have applied before with some changes. In the scenario 1, as ASP and AAP being a combined planner, the profit will be shared between ASP and AAP. And it is similar to the newsboy problem, and in this case the price that AAP offers to ASP is not at all relevant as they are working as combined frames. Whenever the AAP coordinates the strategy, ASP will share pricing information to the corresponding market demand with AAP. Also, ASP will always order the maximum available capacity from the AAP, which means that higher the price AAP charges to ASP for capacity, the higher will be the price that ASP charges back to the market. And when the ASP is coordinating the strategy, ASP do not communicate any capacity requirement and pricing decisions with the AAP. So ASP will just approach the AAP for a price quote for the capacity schedule. AAP will also determine the price of capacity schedule by doing optimal capacity calculation that will maximize their profit, which is their objective in turn. And when there is independent strategies where AAP and ASP determine their own strategies, they will decide the optimum policies individually without discussing to each other. After analyzing the model with these 4 scenarios, we came up with these results. The center planner situation and the independently competing situation results in almost same performance. So in the independent competing strategy, the capacity that ASP agrees to buy and AAP agrees to sell maximize the overall performance. So this mutually agreed capacity corresponds to an equilibrium situation as if the system is coordinated by a central planner. So this makes both the situation give same performance. In case when the AAP or ASP coordinates the SaaS, whoever coordinates has an opportunity to exploit the information shared by the other player in order to maximize their own objective function, for example, their profit. So the impact of delay and capacity cost to ASP is lower when AAP coordinates SaaS, but it will be highest when ASP coordinates the SaaS setup. The impact of delay cost is higher for ASP as it is close to the market. Hence, the combined share of AAP's profit increases even when there is high delay cost. Considering this, we can conclude that it's better for the ASP to control the SaaS setup over the AAP. To conclude, we have come up with some interesting facts we have learned while reviewing this literature. The delay cost and capacity cost affects the overall SaaS more severely when ASP and AAP follows a coordinated strategy than when they are not at all coordinated. The overall profit of whole supply chain is more when the ASP coordinates the supply chain or AAP coordinating it. Also, it's always better to let the player who is close to the market to control the SaaS strategy. In our case, it is the ASP who is close to the market and they will be maintaining the strategy. Also, whoever is close to the supply chain can gain more profit by exploiting the information for their own benefits. In this literature, there are some factors which are not at all considered. The literature only models a relationship between just one ASP and one AIP. This is actually for simplicity. In reality, one AIP could sell to multiple ASPs facing the same market, and then the scenario will be much more complicated. Also, we considered same rental price for a class of customers which is different from the reality situation. That's all about our presentation, and we would like to thank you for listening. This is Amit and Georgin signing off.